Hello, welcome to this lecture on advanced electric drives. In the last class, we were discussing about the air gap flux oriented vector control of induction motor. We have seen that in air gap flux oriented vector control of induction motor, the torque and flux are not inherently decoupled. In fact, they are coupled. So, if we want to vary the torque by changing the torque component of current, the flux does not remain constant. So, we will discuss more on this topic today, that is air gap flux oriented vector control of induction motor. Air gap flux oriented vector control of induction motor. Now, we have already seen that in air gap flux oriented vector control, the d axis of the reference frame is oriented along the air gap flux vector. So, what we do here is the following, that this is the reference axis, reference of phase A of the induction machine, and let this be the air gap flux vector, and that we symbolize by psi m. And what we do, we orient our d axis along the air gap flux vector. This is our d axis, and we call this to be d m, and the q axis is right angle to the d axis. This is the q axis, and we call this to be q m. And due to this, we can see that the angle between the reference A phase and the air gap flux vector, or the d axis of the reference frame, is theta E m. So, this is the angle of the reference frame theta E m. Theta E m is angle between the air gap flux vector and the phase A axis. Of course, the air gap flux vector is rotating in the space with synchronous speed. Now, we must understand that in an induction machine, all flux vectors are rotating in synchronous speed. Let it be rotor flux vector, or air gap flux vector, or the stator flux vector. However, the angle of the flux vector with respect to phase A axis is not the same. They are all rotating synchronously in the space. The relative velocity between all of them in the steady state is 0, but they subtend different angle with phase A axis of the machine. So, this angle, that is the angle of the air gap flux vector, is theta e, which is different from the angle of the rotor flux vector. And what we do here, we have oriented the d axis along the air gap flux vector. So, due to this special orientation, what we obtain is the following, that psi d m, the air gap flux in the d axis in the reference frame oriented along the air gap flux vector, that is equal to psi m, is the total air gap flux, and psi q m in the air gap flux reference frame is equal to 0, because in the q axis there is no component of the air gap flux. If we project this psi m, this is our psi m, along this q axis, since this angle is 90 degree, psi q m will be equal to 0. So, this is what we have seen in the last lecture, and due to this, we can see that we have something like a DC machine like torque equation. The torque equation that we have seen, T e is equal to 3 by 2 into P by 2 into psi d m into IQSM, and this equation resembles that of a DC machine torque equation, and we can control the torque either by controlling IQS or by controlling psi d m, or the air gap flux in the d axis. However, we would like to keep the flux constant, because it is known that if we change the flux, there will be a delay. The flux cannot be changed immediately, there will always be a delay accompanied by the change of flux. So, we would like to keep the flux constant, and we would like to change the torque by changing the torque component of current. This is called the torque component of current. But we will see actually in the last lecture, in fact, we have already derived this equation, and we have seen that when we change the torque by changing IQS, the flux is also changed. So, in fact, psi dm and IQS in the air gap flux reference frame are coupled. They are not decoupled variable, although the two are in two different axes, they are mutually coupled. If we want to change IQS, psi dm is affected. So, we will just rewrite the equation that we have derived in the last lecture. So, in the last lecture what we have obtained is the following, that IDS m is equal to 1 by 1 plus tau LRP into 1 plus tau RP psi dm by Lm plus omega SL tau LR into IQSM. And here tau R is the rotor time constant, that is equal to LR by RR, and tau LR is the rotor leakage time constant, that is equal to L LR by RR. So, this we have already seen in the last lecture. So, if we see this equation if we see now, in this equation you can see that suppose we would like to keep psi dm constant. Now, if you want to keep psi dm constant, if you want to keep this flux constant, let us say, and we can change the torque by changing the torque component of current. Say for example, we would like to change this quantity. Now, if you change IQS, we have to also change IDS. IDS can no longer be constant, we have to change IDS to keep the flux constant. So, in other words, if you want to change the torque, you should also change IDS in association with the change in IQS to ensure a constant flux. So, this has to be implemented to ensure that there is a decoupling between the torque and flux. So, although there is no inherent decoupling, because if you do not take care, suppose you would like to, in this case, say for example, you would keep this constant, let us say we do not vary this. If we assume that this is constant, let us say, and we go on changing IQS. Now, if IDS is constant and we change IQS, naturally the flux will be affected. Psi dm will no longer be constant. This shows there is a coupling between IQS and psi dm in the air gap flux reference frame. To cancel this coupling, what we have to do, we have to change IDS when we change IQS to control the torque. Now, this is one of the equation. The second equation that we have derived is the equation for slip speed. The equation for slip speed that we have obtained in the last lecture was omega SL, that is equal to 1 by tau R into 1 plus tau LRP into IQSM divided by psi dm by Lm minus tau LR by tau R IDSM. So, usually when we want to transform the DQ variable into ABC variable, in this case the variables are in air gap flux reference frame, we have to use the angle of transformation. We have to transform the variables in the DQ frame into the actual variables in the ABC frame, and in this case the transformation angle is theta em, that we have already discussed, that this is the angle of the transformation. So, this angle of the transformation has to be obtained, and to obtain this angle of transformation we have to find out the speed of the air gap flux vector. And the speed of the air gap flux vector is omega E m. Omega E m is the speed of the air gap flux vector. And to obtain this omega E m, we have to have a knowledge of the slip speed. And omega E m is obtained in the following fashion. If you want to find out omega E m, that can be obtained by adding the slip speed with the rotor speed. The rotor speed can be measured using an encoder or a speed sensor, and the slip speed can be calculated. We can calculate the slip speed using this equation, and if we add these two, we get the speed of the air gap flux vector, and the integration of that will give us the angle of the air gap flux vector with respect to the stationary phase A axis. And this angle can be used to transform the dq variable in the air gap flux reference frame to the physical variable of the machine, that is A, B and C. Now, we will see that how we can implement that in case of a block diagram. So, we will take a block diagram to show this can be implemented. So, what we have here, we have to use a transformation. So, this is our transformation block, in which we can feed our IDSM and IQSM. Now, this we can call transformation block. Sometimes this is also called vector rotator, because this rotates the moving variable into stationary variables, and then the output of this would be the currents, the physical currents. So, this is I star, IB star, IC star, the reference current of the machine, the 3-phase machine. And to have this transformation, we have to use the transformation angle that we are just discussing, and the transformation angle is theta em. But how to obtain IDSM and IQSM? IQSM is the torque component of current that can be obtained from a torque controller. So, this can be obtained from the external source. So, we can obtain this IQSM, but to obtain IDSM, we have to take the help of the flux. So, we have to keep the flux constant. So, what we do here, we have psi d m, and psi d m we can divide by L m. So, what we are trying to do here, we are essentially trying to implement this equation. We are trying to find out IDS from this equation. So, we have to keep this psi d m constant. So, this has to be kept constant, and IDSM becomes a function of psi d m, which is this quantity, and then omega SL, the slip speed, and of course, IQSM is the torque component of current. So, when we want to evaluate IDSM, we have to take psi d m, omega SL and IQSM to find out IDSM. So, that is what we are implementing through this block diagram. So, from psi d m we divide by L m, and then we multiply by a gain block, and this is 1 plus tau r p as per the equation. Then we have summer, and then we have again a gain block, that is 1 by 1 plus tau L r p. This is IDSM, and here we have to add also a component of IQS as per the equation. So, this is tau L r, and this is coming from IQSM, and then the slip speed is also involved here. So, we can add the slip speed, but first of all we have to evaluate what is the slip speed. So, the slip speed is evaluated in the following fashion. We have a block which will have this value 1 plus tau LRP, and this is our IQS, and we have a divider block here. This becomes the numerator, and we have the denominator which is calculated as follows. Now, what we are trying to do, we are trying to find out the slip speed by this equation. This equation will give us the expression for the slip speed. So, when we want slip speed, the slip speed can be used in the first equation. If this is our equation number 1 and this is equation number 2, the first equation, to find out IDSM, we need slip speed. So, we have to evaluate slip speed. So, this is how we are evaluating the slip speed, and this will be coming from the flux, and then the other component is coming from IDS. We have again a gain block here, tau LR by tau R, that is obtained from this gain block, and this is IDSM which is fed from the upper current, that is the flux component of current, and then this becomes the denominator. So, what we are doing here, we are basically evaluating the denominator, that is psi dm by Lm minus tau Lr by tau R into IDSM. That is what we are evaluating here, and then this becomes the slip speed. The result here is the slip speed, and when we have slip speed, we can use this slip speed in various ways. First of all, this slip speed is taken and we can add to this slip speed the rotor speed. We can add here the electrical speed of the rotor omega r, and what we obtain here is omega em, is the speed of the air gap flux vector, and when we integrate this, what we obtain is theta em. So, this one, when we integrate this one, we can have a integrator block here. We can integrate this speed to obtain the angle of the transformation, that is theta e. And this slip speed which is calculated here is also used for evaluating IDSM, because we have seen that the slip speed in this case is required to evaluate IDSM. So, in this we can take this slip speed and put the slip speed here that we have evaluated here. We can in the block here, we can multiply the slip speed. In this case, we have a gain block, and then finally this is helpful in evaluating the flux component of current, that is IDSM. Now, this is the block diagram of air gap flux orientation. Now, we must understand that air gap flux orientation is computationally intensive, because this requires a lot of signal processing, and this block which is shown in a dashed enclosure, we can show this in a dashed enclosure, this part of the circuit, can be termed as a decoupling block. So, we can say this as a decoupling circuit, because this decouples the inherent coupling present between the torque component of current and the air gap flux. So, if we have this signal processing outside the transformation block, we can cancel the coupling that is present in case of air gap flux orientation, and when we change the torque or the torque component of current, the flux can be maintained constant. So, what you have to do is that if you want to keep flux constant, we can say that this is our flux. So, we can say this remains constant. So, we can keep this constant, and we can go on changing the torque component of current. This is our torque component of current. So, we can change IQS, and if we give a constant flux command, flux will be constant, because this decoupling network or the decoupling circuit takes care of cancelling the coupling present inside the machine. So, of course, we have already understood that the air gap flux is easy to measure, but the price that we have to pay here is that the coupling is present, and to cancel the coupling inside the machine, we have to use a decoupling circuit or a decoupling network. We can go one step ahead. The argument is we can orient the reference frame with respect to the rotor flux. We can orient the reference frame with respect to the air gap flux. Why can't we orient the reference frame with respect to stator flux? There are some researchers who have tried to do stator flux orientation. The advantage of having stator flux orientation is that the stator flux is the easiest flux to be measured. The measurement of stator flux is the most easy. So, this is one of the motivations to go for stator flux orientation. So, here after this we will be discussing about the stator flux orientation. Stator flux oriented vector control. Now, in this case also we can say that if this is our phase A axis, is a reference A, and what we are doing here, we are tracking for the stator flux. This is our psi s, and what we do here, we orient our d axis along the stator flux vector. So, we can orient our d axis along this. So, we call this to be d E s, symbolizing that this is a rotating reference frame and this is a stator flux reference frame, and the q axis is orthogonally oriented along the with respect to the d axis. So, this is our QES, and if we see, this is our reference frame, or this is the reference phase A axis, and this angle is theta EES. This is the angle of the stator flux vector with respect to the stationary phase A axis. So, here also we can very comfortably say, because of the orientation, we can directly say that psi ds E is equal to psi s, total stator flux vector, and psi qs E is equal to 0. Due to the proper orientation, we know that there is no component along the q axis, and the torque can be written in the following fashion: T E is equal to 3 by 2 into P by 2 into psi ds Es I qs Es minus psi qs Es into I ds Es, and we have assumed that this is equal to 0. So, if we assume this psi qs equal to 0, we can write this equation as 3 by 2 into P by 2 into psi ds Es into I qs Es, and this also resembles the torque equation of that of a DC machine. So, this equation has got only two variables, that is psi ds and psi qs. So, we can keep psi ds constant, as we have seen in case of air gap flux orientation. We can keep psi ds constant and we can change IQS to control the torque. But however, in this case also, just like our air gap flux orientation, the torque component of current and the flux are inherently coupled. It means we cannot control these two variables independently. If we control IQS, psi ds will be altered. So, we have to have a decoupling circuit to cancel the inherent decoupling present in the torque component of current and the stator flux in the d axis. So, likewise also we can derive the equations, and the equations can be derived in the following fashion, that we can write down the expression for the rotor flux in the d and q axis in terms of stator flux. Psi ds Es minus LLS IDS plus LLR IDR. And similarly, we can write down the rotor flux in the q axis in terms of the stator flux. Now, this is necessary because we target the stator flux vector LLS IQS plus LLR IQR. So, what we are trying to do here, we are trying to write the rotor flux in terms of stator flux psi ds and psi qs. Now, we know that psi qs is equal to 0. So, if you substitute this in this case, we can get the following expression for psi qr LLS IQS plus LLR IQR. Now, similarly, we can also write down the expression for the rotor currents. In this equation, the rotor currents are not known. So, these currents are not known here. So, we do not know this current IDR, we also do not know IQR. So, we have to express this rotor current in terms of stator current and stator flux. So, we can write down expression for IDR and IQR in terms of stator flux and stator current. So, we can do that in the following fashion. IDR ES, that is equal to psi ds ES minus LS IDS by LM, and in a similar fashion we can say that IQR ES, that is equal to psi QS ES minus LS IQS ES by LM. And we know that this flux does not exist, this equal to 0. So, we can further simplify this equation for IQR, that is equal to minus of LS IQS ES by LM. So, we have expression for the rotor fluxes, we have expression for the rotor currents. Now, we can derive the equations starting from the rotor voltage equations. So, as we have done in case of an air gap flux oriented control, similarly we can derive the expression for the flux component of current and the slip speed for stator flux oriented vector control. So, we can start that from the rotor voltage equation. So, we write down the rotor voltage equation in stator flux oriented reference frame. And here we can start with the d axis VDR ES, that is equal to 0, and that is equal to IDR ES RR plus piece IDR ES minus of omega SL into psi QR ES. So, this is as we have done in case of a rotor flux oriented vector control. We can write a similar equation, but we have to express psi QR in terms of psi QS. So, here in this equation what we do two things. First of all, we take this first term IDR ES, and this IDR in fact we do not know, we have to express IDR, and IDR expression is already available here, already we have the expression for IDR. So, we know what is IDR. So, we can have the expression for IDR and write this IDR here, that is psi ds ES minus LS IDS ES divided by LM into RR. And what is psi dr? Psi dr we can express it in terms of psi ds, that is psi ds ES minus of LLS IDS ES plus L LR IDR ES. And then we have psi QR, and psi QR can be written in the following fashion: omega SL into psi QS ES minus L LS IQS ES plus L LR IQR ES. So this equation can be simplified, and the scope of simplification exists here. What we can do in this case is that this quantity does not exist, so we can put that equal to 0, and we can substitute for IDR. IDR is not known, so IDR can be written from this equation, and then we have to substitute for IQR, and IQR is given by this expression. So we can substitute for IDR and IQR and further simplify this, and we get the following expression. So if we simplify this, what we obtain is the following: 0 equal to psi ds ES minus LS IDS ES by tau r plus P psi ds ES minus L LS LR plus L LR LS by LR into P IDS ES plus L LR by LR P psi ds ES minus of omega SL into psi QS vanishes. So we have minus of L LS LR plus LR LS by LR into IQS ES. Now this equation shows there exists a coupling between IQS and psi ds. Now suppose we would like to keep psi ds constant. Now if you want to keep psi ds constant, and if this quantity is kept constant, but yet we have to control the torque, we can control the torque by increasing or decreasing IQS. IQS is the torque component of current. Now if we keep this, or if we change IQS and we would like to keep the flux constant, we have to change IDS. Unless we change IDS, as we change IQS, the flux IDS will change. So what we do here, to keep the flux constant, we have to change IDS as a function of IQS, slip speed in this equation. So what we have to do here is the following: we can write down from this equation IDS as a function of psi ds, IQS, and the slip speed, which we can easily write as we have done in case of an air gap flux oriented vector control. So if we obtain psi ds IDS as a function of psi ds, IQS, and omega SL for a given omega SL, for a given IQS, and for a given psi ds, we can evaluate what should be IDS. Similarly, if we take the Q axis rotor equation, in the stator flux reference frame, we get the following after simplification. So what we can do here, that this is the rotor flux rotor equation plus P psi QR ES plus omega SL psi dr ES. Now we can simplify this. Now once we simplify, we get the following result: LS by tau r into IQS ES minus LS by LS plus LR by LR LS P into IQS ES plus omega SL into psi ds ES into 1 plus L LR by LR minus L LS by LS plus L LR by LR into LS into IDS ES. This equation is definitely more involved, because this has got the derivative term like what we see here. This also has got the expression, I mean the variables like IQS, variables like IDS. So, this equation after simplification we can get the expression for omega SL. So, from this equation we can evaluate omega SL. So, what we have to do here is that we can evaluate omega SL from this equation. Okay. So, this omega SL can be evaluated from this equation, and after we evaluate omega SL from this equation, this omega SL can be used to compute the speed of the stator flux vector, which will be used for the transforming IDS and IQS into IA, IB and IC. We are discussing about the stator flux oriented vector control, and we have seen that there is inherent coupling between the torque component of current and the stator flux. So, we have to cancel the coupling by having a decoupling network. We have two equations here. This is the first equation. We can say this is equation number 1. So, in which we can obtain IDS in terms of psi ds, IQS and the slip speed, that is omega SL. And we have the second equation here, which will give us the expression for the slip speed, that is this quantity. So, from this we can evaluate what is the slip speed. So, we can use these two equations to implement air gap flux oriented, stator flux oriented vector control. So, we can see how it is implemented. So, what we have to do here is that we have to transform the variables from the stator flux reference frame, and here we have IDS and IQS, and we have to use the transformation here, and this transformation is basically done using the angle of the stator flux vector, that is theta E ES. Now, if we see this angle is the angle that we are talking about. This angle is used to transform the variables in the stator flux reference frame into the variables in the stationary ABC reference frame, that is phase A, phase B and phase C. So, we have to find out this angle, and to find out this angle theta E, we need the information about the slip speed. So, this is evaluated by integrating the speed of the stator flux vector, that is omega EES, and that is obtained by the summation of the actual speed, that is omega r, and the slip speed that is calculated using equation 2 by using this equation. So, we can calculate the slip speed using this equation, and this slip speed can be used to compute the synchronous speed at which the stator flux vector is rotating in the space. We have to use here what is called the slip computation block. So, this is the slip speed calculation, and this we write, this is equation 2 that we have previously shown. We have the equation 2. This equation 2 will give us the expression for omega SL. And what are the inputs here? The input to this slip calculator or the slip calculation block are IDS, IQS, and of course psi ds. And then we have here a decoupling network, as we did in case of an air gap flux oriented vector control. So, this is the decoupling network. And this decoupling network is basically obtained from equation 1. IDS is evaluated as a function of the d axis stator flux, the q axis current in the stator flux reference frame, that is IQS ES, and the slip speed that is evaluated using the slip calculator. So, we can use that in the decoupling network. So, what we have here is psi ds ES, and if we want to keep it constant, we can give a constant reference here, and then here we can have the IQS. This is the torque component of current. This current usually comes from a speed error. So, we have a speed error, and then we have a PI controller which basically gives us the torque component of current IQS. And psi ds, we can choose to keep this constant. If we want constant flux operation, we can keep this constant. And what are the other inputs here? The other input is the slip speed, that is omega SL, because we have been able to evaluate IDS as a function of the stator flux, psi ds, IQS, and omega SL. So, these are the input to this block, and that is called the decoupling block. And out of that we obtain IDS, and IQS goes directly. In this case, there is no transformation so far as the IQS is concerned. And then after this transformation from IDS to IQS using theta E, what we obtain here is the reference 3-phase current IA, IB, IC. They are the reference current. So, we can denote them as IA star, IB star, and IC stars. And the reference currents that we have can be impressed on the machine using an inverter. So, here what we have here to inverter control. So, we can use a voltage source inverter. We can have an induction motor here, and these are the 3 different phases of the induction machine. So, we can have this inverter, and this inverter will impress this IA star, IB star, and IC star to the 3 phases of the machine. They are phase A, B, and C. So, we can have a sensor here. We can have a speed sensor, and the speed sensor will be giving us the mechanical speed omega m, and this we can multiply by the number of pole pair p by 2 to get the electrical speed. And this is fed here, and this is added with the slip speed to obtain the speed of the stator flux vector, that is omega E superscript ES, and integration of that will give us the angle of the stator flux vector, and the angle in this case can be used to transform IDS and IQS into IA, IB, IC, which will be impressed onto the machine by using the inverter. So, this is something similar to that of the air gap flux oriented vector control, and this is also little bit more complex, because you know that we have to use this decoupling network. So, unless we have this decoupling network, we cannot go for vector control using stator flux reference frame or air gap flux reference frame, and this decoupling network makes it computationally more intensive. So, what we have to have a very fast online processing of all the signals. We have to have a digital processor to process the signal in real time, so that this can be over so quickly that the control is implemented within a short time. So, this is about the stator flux oriented vector control, which requires a decoupling network. We will now discuss about an interesting area of modern AC drive control, that is the speed sensorless control, and we will see how the speed sensorless control can be implemented in an induction machine. Of course, whenever we want a drive, we have to have very often, in fact, we go for a closed loop speed feedback. We want a variable speed drive. We would like to control the speed as we want, and for that we have to have a closed loop speed feedback. And for the closed loop speed feedback, we often use a speed sensor, which could be an encoder as well. But the speed sensor makes the system less robust, and in many industrial applications, the speed sensor may not be desirable. So we will be discussing the speed sensorless vector control. So the objective in this case is that we have to eliminate the speed sensor, and hence it is called speed sensorless. So we have to estimate the speed. So the basic idea in this case is estimation of rotor speed. And how do you estimate the rotor speed? We estimate the rotor speed from terminal variables. So estimation of rotor speed from terminal variables. Now what are the terminal variables? Suppose we have an induction machine, and these are the three phases of an induction machine, and what is available to us is the three terminals, okay? And in this case we can have the currents and the voltages. So the terminal variables are in fact the current and the voltages. So we have to estimate the speed from current and the voltages of an induction machine. Now to be able to do that, we have to have some equation. So we will derive some equation and show how we can go for speed estimation from voltages and currents. So the first one, we will take a stationary reference frame, and we can write down the equation of the voltages in the stator. This is the d axis stator voltage, VDS equal to RS IDS plus P IDS, and VQS is RS IQS plus P IQS. And we can express this flux in terms of current. So what we can do here is that we can say, for example, in the d axis we can say that psi ds equal to Ls IDS plus Lm into IDR. And what is IDR? Again, we do not know what is IDR. IDR is the rotor current, and the rotor current is not easily available to us. So we have to replace for IDR. So this IDR has to be replaced as we have done before. That is equal to Ls IDS plus Lm into IDR is psi dr minus Lm IDS by Lr. So this is our IDR. Now if we simplify this, we can get the following expression: Ls minus Lm square by Lr into IDS plus Lm by Lr into psi dr. This is what we obtain here. And then as before, we can say that that's equal to Ls into 1 minus Lm square by Ls Lr into IDS plus Lm by Lr into psi dr. That's equal to the leakage factor sigma into Ls into IDS plus Lm by Lr into psi dr. This quantity is called the leakage factor. This is called the leakage factor because this is actually an index or a measure of the leakage inductance of the machine. if the leakage inductance is 0 or the coupling is tight between the stator and the rotor, the leakage factor will be 0, which is of course hypothetical. There is always some leakage inductance. The sigma is a small value, it is called the leakage factor. So exactly in a similar way we can write down for the q axis. So we can say here that in a similar fashion we can say here psi qs is equal to sigma into ls iqs plus lm by lr into psi qr. So we can substitute this in the stator equations and simplify the stator equations. So we can say the stator equations that we have already written, VDS is equal to RS IDS plus P psi ds. So we can replace for psi ds as we have derived. So that's equal to sigma ls P IDS plus Lm by Lr P psi dr. This for the d axis, and similarly in the q axis we can say that VQS is equal to RS IQS plus sigma ls P IQS plus Lm by Lr into P psi qr. So these are the two equations for the stator, and similarly we can write down the equation for the rotor. The rotor equations in the stationary reference frame would be 0 is equal to RR IDR plus P psi dr plus omega r into psi qr. This is in the d axis. Similarly we can have in the q axis as well. 0 is equal to RR IQR plus P psi qr minus omega r psi dr. So these are the two equations in the rotor. So what we will do again, we can eliminate the rotor currents. These are not known to us. IDR is not known and IQR is also not known, and then we will do some simplification, and from the stator and the rotor equation we will try to estimate the rotor speed, that is omega r. So in a way what we are trying to do here, we are trying to estimate the rotor speed from the terminal variables, and the terminal variables are the voltages, VDS, VQS and IDS and IQS. In the next lecture we will see that how we can have a block diagram, how we can implement this in the form of a block diagram to estimate the speed from the terminal variables VDS, VQS, IDS and IQS.